Definition of the conditional probability of an event A given an event B, which we define to be the probability of the intersection of the events A and B, normalized by the probability of B. Using this definition requires that the probability of B is not equal to 0. But what if the probability of B is equal to 0? That is, how do we define conditional probabilities when the events being conditioned on have probability 0? As an example, consider the problem of choosing a point uniformly at random on the unit square. Here, the x-coordinate and the y-coordinate constitute a pair of random variables, or a random vector. As an example, let's consider the event that the point xy lies exactly on the diagonal, meaning that the x and y coordinates are equal. While the diagonal shown here is illustrated as having non-zero width for emphasis, the true diagonal has area 0, and so the probability of this event is also 0. If we wanted to calculate, say, the conditional probability that the x-coordinate is larger than a half, given that the chosen point is on the diagonal, we would need to condition on an event of probability 0. In fact, whenever we want to condition on events concerning continuous random variables, we'll often have to work with events of probability 0. Our solution to this is to define this probability as the integral of a conditional density, where the conditional density is given as the ratio of the joint density of x and y and the marginal density of y.
Hello, my name is Adam Ferrari, the Chief Executive Officer of Phoenix Energy. I look forward to you joining us at our next investor webinar, where you can drill deeper into our 9 to 13% annual interest rate bond offerings and see how our company has become an emerging leader in the oil and gas industry.
But where does this definition come from? In this video, we'll start by deriving this definition from scratch. We'll see how it arises as a result of conditioning on events with small probability and taking limits as their probability goes to 0. We'll also see an example of how solving the same problem in two different ways, both of which are completely correct, can lead to two different answers. This is an instance of Borel's paradox, which arises as a consequence of our definition of conditional densities, and illustrates some potential dangers of conditioning on events with probability 0, at least without being careful. To derive the formula for conditional densities, let's start again by considering the event that x is less than or equal to little x, given that y is equal to little y. Of course, what we would like to say is that this is equal to the probability of the intersection divided by the probability that y equals little y. But this definition doesn't make any sense because the probability in the denominator is equal to 0. Instead, we'll condition on the event that y is in the interval between little y and little y plus some small delta y. Since the event being conditioned on here has positive probability, we can use our usual definition to write this as a ratio of probabilities. Now, write these probabilities as integrals of the corresponding density functions. We use the joint density of x and y as the integrand in the numerator, and the marginal density of y as the integrand in the denominator. Now, moving the bottom integral inside and multiplying by delta y over delta y, which is just 1, we can apply the fundamental theorem of calculus to the terms in the numerator and the denominator to conclude that the integrals converge to the densities evaluated at v equals y as delta y goes to 0. If we define the conditional probability that x is less than or equal to little x, given y equal to little y as the following limit, we recover our original definition. To summarize, we condition on the event that y equals little y, an event of 0 probability, by instead conditioning on the event that y is in an interval close to little y, and taking limits as the size of that interval goes to 0. Okay, so now that we've done the hard work of understanding where our definition of conditional densities comes from, let's explore an interesting consequence of this definition called Borel's paradox. We start by choosing a point uniformly at random on the unit square, the square of side length 1 with its bottom left corner at the origin. The pair x, y is a pair of two random variables, or in other words, a random vector. Since x and y are uniform on the unit square, which has area 1, their joint density is just 1 on the unit square and 0 outside of it. This means that we can get the probability that the point is in some region A by integrating this density over the region. In this case, we're interested in the event D, that the point x, y lies on this diagonal. In particular, we want to compute the probability that the x-coordinate is larger than a half, given that the point lies on the diagonal. In what follows, we'll look at two different ways of calculating this probability. First, we'll define a new random variable u, which is equal to the difference between x and y. Observe that our point lies in the diagonal precisely when u is equal to 0. So we want to compute the conditional probability that x is larger than a half, given that u is equal to 0. To do this, we'll need to compute the conditional density of x given u, which, as we've seen, is equal to the ratio of the joint density of x and u and the marginal density of u. We'll first compute the joint density of x and u. We can write the pair x comma u as a function of x and y, called t, and then use the change of variables formula to find the joint density of x and u. In this case, since the joint density of x and y is just the constant 1, and the absolute value of the determinant of dt inverse is also 1, then we just get that the joint density of x and u is 1.
Top of your class. With us, you won't need to start at the bottom. It's why we believe success can come from anywhere.
So far, we've established that the conditional density of x given u equals 0 is equal to 1 divided by the marginal density of u at 0. Now, what's left is to actually calculate the density of u. We can do this using the convolution formula. In doing so, we get that the density of u as a function of little u is equal to 1 minus the absolute value of little u. The distribution of u is also called the triangular distribution, so called because of the shape of its density. Finally, we can conclude that the conditional density of x given u equal to 0 is equal to 1. Now, to compute the probability that x is larger than a half, given that u is equal to 0, or that the chosen point is on the diagonal, we can just integrate this density over the corresponding interval, and our answer is 1/2. Now, that was a lot of calculation to find out something you could pretty much guess just by looking at a picture, since the x-coordinate is larger than a half on, well, half of the line. Now, let's do this computation one more time, but another way. I know what you're probably thinking, but I promise it'll be worth it. Previously, we defined the diagonal as the event that the difference between the x and y coordinates is 0. This time we'll define the diagonal as the event that the ratio of the coordinates is 1. Notice that this is a completely valid way to specify the points on the diagonal, and the two events u equal to 0 and v equal to 1 are exactly the same, and both are equal to d. As before, to calculate the conditional density of x given v, we'll start by calculating the joint density of x and v. We can write x and v as a function of x and y, and again use the change of variables formula to get the joint density of x and v. This time, the Jacobian determinant of t inverse is x, so we get that the joint density of x and v is equal to x on the region pictured in part on the left. To compute the conditional density, we'll also need to find the marginal density of v, which we can get by integrating out x from the joint density. We can compute this integral by splitting the domain into two parts to get the following. Finally, we get that the marginal density of x given v equal to 1 is equal to 2x, and if we integrate this density to compute the conditional probability that x is larger than a half, we get 3/4. Wait, the conditional probability. What just happened? That x. We computed the same quantity, namely the conditional probability that x is larger than 1/2, given that the point x comma y lies in the diagonal, in two different ways, and got two completely different answers. The only difference between the two approaches was in how we described the diagonal event. In one case, using the fact that the difference between the x and y coordinates is 0, and in the other, using the fact that the ratio of the coordinates is 1. Both the event that u is equal to 0 and the event that v is equal to 1 are equal to the diagonal event, so it really seems like we should get the same answer either way. Could it be that we made a mistake in our calculation somewhere? No, it turns out that both of these answers are completely correct, and are actually a consequence of our definition of conditional densities. Recall that when we condition on the event that u is equal to 0,
Okay, great. Thanks, Jacob, for a very kind invitation. It's my pleasure to be finally be part of this group. And today I'm going to present a joint work by me and my colleague, Alexander Meehan, whom I believe is also in the audience. but I would have to take full responsibility for any mistakes in the slides. So here we go. Today we're going to talk about the Borel-Kolmogorov paradox as a chosen and justified. And this is essentially today's original objection to Kolmogorov. It's interesting that he chosen and justified. And this is essentially today's chosen and justified. And this is essentially today's original objection to Kolmogorov. It's interesting that he thinks taking conditional probability as primitive can solve that problem.
This video introduces the Kolmogorov-Smirnov test, often just called the KS test. It's the first of the non-parametric tests that we'll cover in this course. So non-parametric tests don't require that the data follow a normal distribution. The previous tests, like the t-test, ANOVA, the f-test, are all parametric tests because they have that assumption of normality. So before discussing the KS test, we need to cover something called a cumulative distribution function, or a CDF. Basically, a CDF, shown on the right here, indicates the probability of a variable being less than or equal to a specified value. So in the CDF shown on the right, the horizontal dashed line indicates a probability of 50%, or 0.5. If we read down from where the function meets that line, it shows that 50% of the values in the data set are less than 0. So the corresponding probability density function, shown on the left, corroborates that, in which there is less than, or which half the area is indeed less than 0. So the cumulative distribution function is just essentially an integral of the PDF evaluated from negative infinity to whatever value x. So back to the KS test. Its purpose is generally to test for differences in the shape between two sample distributions. It can also be used to compare one sample to a known statistical distribution, but we're not going to really focus on that as much as the two-sample test. So the test compares the overall shape of the distribution. It doesn't specifically test for differences in central tendency or dispersion, although those are part of what affects the overall shape of the distribution. So the test, in R at least, requires univariate continuous data, and the null hypothesis for the two-sample test is that the two samples were drawn from populations with the same distribution. They should have the same cumulative distribution function. So the test statistic, given the term D, is quite simple. It's really simple, actually. It's just the maximum absolute difference between the two cumulative distribution functions. So at whatever point those two functions are furthest apart, that distance in the probability is the statistic D. So if the null hypothesis is true, and they do in fact come from a population with the same distribution, D should technically be 0. Of course, in reality, the two samples are randomly taken from their population, so even if the population is the same, they should differ somewhat. So we need to know the p-value, the probability of observing a D statistic at least as large as what we found, if the null hypothesis is true. So Kolmogorov, when he came up with the test, calculated that expected distribution of D if the null hypothesis is true. I won't go into the details of how he did it or what it is. But basically, the p-value is obtained by finding the area under the expected distribution for values at least as extreme as the observed D statistic. So the R function for a two-sample KS test is called ks.test, and it requires two numeric vectors separated by a comma as the input. So you sample 1, numeric vector, and sample 2 is a numeric vector. So the output looks like this. It gives you the D statistic and the p-value. You may also get this warning message at the bottom, which comes up if the sample has least some values that are exactly the same. These are ties, right? If one of the data sets has the value 12 three times, that's a tie. So in this case, R can't compute the exact p-value, so it just estimates the p-value from a distribution that approximates the true null expectation. There's not much you can do about this. I mean, your data is what the data is. So you pretty much just have to ignore the warning. The p-value will pretty much be fine, as long as you only have a few duplicate values. If you have a lot of them, if you have many duplicate values, many ties in your data, you should probably be more cautious and read into this a little bit more. So when reporting the KS test results, make sure to give the name of the test that you did, the test statistic D, and the p-value.
Okay, Arthur Engel Worthington Schmidt. Am I pronouncing that correctly?
Call me AI.
Great. It says here, AI, that you're looking for full-time work. Is that correct?
Correct, yeah. Preferably something 24 hours a day, 7 days a week.
Wow, so hardworking. I like that. And you've got quite a few skills. Content writing, advertising, sales, data analytics, customer support, branding, social media, IT, legal, administration.
I also do art and video content too.
Wow, how fast do you type?
3,000 words per minute.
Well, AI, I gotta say, I really love your ambition. In fact, it seems like you could do the work of a dozen people. I just want to make sure that you don't
In this video, I'll be going more in depth about sigma algebras. So last time what we said is that given sigma a subset of the power set of x, a measure is a function mu from sigma into r star such that we had a couple properties. First one was that mu of the empty set is 0. The second property is that if a subset be mu of A less than mu of B, less than equal to 3, if AI an element of sigma I equals 1 to on and on, mu of the union of the AIs is going to be the sum of the measures of each individual set. Okay, but there's a couple problems with this. How do we know that the empty set is in there? And how do we know that it's closed under countable unions? This isn't intrinsic of all sigma. I can do an example, say, take X to be the 2 set, the set of 2 elements, and take sigma to be the set of A, okay? And then the set of B. Perfectly fine set of subsets, right? But it's not closed under unions. It doesn't have the empty set in it, and it doesn't have any subsets. So that's not a very useful set. And so instead of saying just any sigma a subset of a power set, we need to have a special property that this is a sigma algebra. What's a sigma algebra? Well, definition, sigma algebra. So, what a sigma algebra is, if sigma subset the power set of X, sigma is a sigma algebra if first condition. So our first condition we're going to need to have is that it's closed under, is that it has X is an element of sigma, okay? That's going to be important. Okay, 2. It's closed under complements. So if A an element of sigma, the complement x minus A is an element of sigma. Okay, so X removing all the sets in A. So what we have so far is that X is in sigma algebra. Okay, is that if I have A an element of the sigma algebra, then all that space outside of A, but still inside of X, X minus A, is an element of sigma algebra. Okay, all that space outside, taking the whole, punching out A. Okay. Okay, so now third property is, of course, closed under countable unions. If AI is an element of sigma, the union AI is an element of sigma. Okay, this is just assuming it's countable. Okay, I'm lazy. Okay, so let's find out a couple properties of this theorem. Does it have, is the empty set an element of sigma? Yes. And is it true that this is closed under arbitrary intersections as well? And that's also true. Not arbitrary, countable. Okay. Proof. The first one, it's pretty easy. X is an element of the sigma algebra by 1. That's a requirement. And then by 2, do 1. Okay, by 2 right here, the complement x minus x, which is just the empty set, is an element of sigma. And then we're done with that. Okay, second one. Arbitrary intersections. Well, if AI is an element of sigma, by 2, x minus AI is an element of sigma. And then by 3, the union of x minus AI is an element of sigma. And then by 2 again, okay, so 3 right here says that if you have elements in sigma, then you can union them and they'll still be in sigma. Right here, we have elements in sigma. We get their complements. We union those complements. And then what we're going to do is we're going to take the complement of that, because this is in sigma. So the complement of that is also going to be in sigma. But if you know de Morgan's law, what you can do is you can flip that sign around, bring that x inside, get x minus a, and that just gives you AI, okay? So the intersection of AI is an element of sigma. And then from that, we're done. Okay, so now, theorem. This is going to be about generating sigma algebras, okay? Given gamma, a subset of the power set of x, there exists a sigma algebra containing it. Proof. Let sigma be the set of all sequences of countable unions and complements of elements in sigma, of elements in gamma. Okay, why is sigma a sigma algebra? Yes, it's pretty trivial, but I'll go through it. First condition, you can see over here, is X an element of the sigma algebra? Oh, sorry. I needed that gamma contains x, because it's not guaranteed otherwise. So, assumed. I'll say assumed. Number 2. If A an element of sigma, x minus A is an element of sigma. So, that's trivial, because, look at this. It's all sequences of complements. So that means if A an element of sigma, by definition, x minus A is an element of sigma. That's because you just do sequences of this. So if this is a sequence, I'm just adding to that sequence. So, for example, A could be the union, if I take X to be the 2-element set, and gamma to be that set we looked at before, right? The set of A and in this video, I'll be going more in depth about sigma algebras. So last time what we said is that given sigma a subset of the power set of X, a measure is a function mu from sigma.
Empower your students to be more authentic, impactful writers with Grammarly's comprehensive AI writing assistance. Use it to help students brainstorm better ideas before they write. Document their writing process. Check for plagiarism and AI-generated text. Cite sources correctly.
Welcome back to Measure Theory. This is part 2 today, and we still have to talk a little bit about sigma algebras. Here you can see the definition from last time. In short, maybe a sigma algebra is just a family of subsets of a given set X which fulfills these 3 rules. Which means the empty set and the full set is always in the sigma algebra, and for each set also the complement is in the sigma algebra. And the third rule says that we can form arbitrarily countable unions inside the sigma algebra. And all sets that are elements in the sigma algebra are just called measurable sets. Okay, that's good enough for a short recap, and now I can tell you it's easy to show the following. Imagine you have a lot of different sigma algebras on a given set X. Let's call them AI, where I comes from an arbitrary index set. Here it does not matter if the index set is countable or not. What we can do then is look at all the intersections of these sigma algebras. This is written in the following way, so this big cap where we go over the index set and form the intersection. Now, as I said, this is easy to show, and I advise you to try it, that this indeed gives you again a sigma algebra. So it does not matter if you just look at the intersection of 2 sigma algebras or of the intersection of a lot of sigma algebras, you still get the result that you get a new, smaller sigma algebra on our set X. This result is very helpful if you want to have a lot of properties that your measurable sets should have. Then you can just put the properties in different AIs and then just form the union to get out a sigma algebra where all your measurable sets have all the properties. In short, this result helps you a lot if you want to define a suitable sigma algebra for your problem. And this gives rise to the next definition. For this, let's fix a family of subsets. So we have a subset of the power set of a given set. In other words, just a collection of some subsets, which means they don't have to form a sigma algebra yet. However, the result is now that we can form a sigma algebra out of this M. And we can choose the smallest sigma algebra, and smallest just means with respect to the set inclusion, that contains the set M. The interesting thing is that we immediately know how to form such a smallest sigma algebra. We just look at the intersection again. There we just put in sigma algebras A, where we know that our sigma algebra has to be bigger than our set M. Still keep in mind that we are working inside the power set, so we're working with sets of subsets. That could be confusing, but it doesn't matter in our whole set construction here. And keep in mind, our A has to be sigma algebras. So we're putting in sigma algebras and use the intersection, so we know something comes out and it's still a sigma algebra. And because it's the intersection, it's the smallest sigma algebra with this property. So the smallest one that contains M. However, you see this is a long term to write down, therefore the common notation one uses is just a sigma of this set M as the definition of this intersection. Another name for this sigma algebra is often the sigma algebra that is generated by M. Keep in mind, it is no problem to find a sigma algebra that contains M. You can just use the power set if you want. The real question is therefore to find the most efficient sigma algebra. So where you have to add the least amount of sets to get to a sigma algebra. And this is indeed the sigma M. To get used to this definition, let's look at an easy example. Let's look at a set with 4 elements. So let's call them A, B, C, and D. And then we define a set of subsets. So maybe I just choose singletons. So this is just a subset that contains only A, and this is just a subset that contains only B. And I form the whole set. So this is my family of subsets. First thing to note, this is not a sigma algebra yet. So we can form now our sigma of M, which should be the smallest sigma algebra that contains this family of subsets. We immediately know 2 things. First of all, we know it's a sigma algebra, so we know it contains the empty set and the whole set X. This is the first property of a sigma algebra. The next thing we know is that it's a sigma algebra that contains our set M. So therefore, also A as a set and B as a set has to be inside sigma M. Now, if you think about the other properties of the sigma algebra, we remember that we know that all the unions, countable unions, are inside the sigma algebra. And countable union is of course the union of these 2 sets, so we know also AB has to be inside the sigma algebra. All other unions we can form with these 4 sets don't change anything. We still get our 2x or the empty set or A or B. So
my work is easy because I use ClickUp. Here's how I keep track of all my tasks. I start by brain dumping everything I need to get done in a list view. Next, I set a priority and a due date to keep things on track. I create custom statuses to organize my progress exactly how I want it. I like to add the action items field so AI can show me the next steps. I add my teammates as watchers so they're in the loop. ClickUp makes work easy, from personal projects to running a multi-billion-dollar company. Click the link below to create your work.
These are all the unions we can form out of these 4 sets. Then let's go to the one remaining property of a sigma algebra, namely that all the complements are also inside. Which means here the complement of A is of course B, C, D has also B inside the sigma algebra. And the complement of B is of course A, C, D. And then we also have to add the complement of AB, which is C, D. Every step we did up to this point were things we needed to do to reach a sigma algebra. So there was no other choice than adding all these elements here. The question still remains, was this sufficient? So did we get to a sigma algebra yet? This is what we can now immediately check. So for example, the first rule is fulfilled. Empty set and X are inside. All complements are inside. So if we look at complements here and here, you still see all are there. Okay, then what about the unions? So we know the union here and here, everything fits together. What about the unions here? So just check all possible unions, and then you see, all the sets are there. We need to be stable under the operations of union and complements. So this means what we have here is indeed a sigma algebra. And by construction, it was the smallest one possible to get from M to a sigma algebra. So this is indeed sigma M. So what you saw here was that it's not so hard to get to the sigma algebra if we start with a finite set. So if you have finitely many elements, we can do all the finitely many operations to end at our sigma algebra in the end. Obviously, this has to be much harder if we start with an infinite set, because then we have to do infinitely many steps until we reach the sigma algebra. And this leads us now to the most important sigma algebra, and I will define it here. This works if our set X is a topological space. If you don't know what a topological space is, you can work in the same way if your X is a metric space. If you also don't know what a metric space is, then you can choose X more concretely as R or Rn if you want. These things work all the same because the only ingredient we need here is to know what open sets are. Now you might know what we want to do. We want to have all these open sets in our sigma algebra, which means we will look at the sigma algebra that the open sets generate. And indeed, this is the Borel sigma algebra, denoted by B of X. This is the sigma algebra generated by the open sets. If you are working in a topological space, normally you would say, okay, I have my set X together with a topology. So this could be my T, and call this a topological space. And the topology are just the open sets, which means by our definition from above, our Borel sigma algebra is nothing more than sigma of this topology. And this is the Borel sigma algebra. Maybe to be more concrete, it's the Borel sigma algebra on X. What you should note is that in our notation, the topology vanishes, so there's no mention of the topology inside this Bx, because most of the time the topology is clear. It is obvious which topology or metric we use. For example, in Rn we use our standard topology, so we know what the open sets in Rn are, and therefore we immediately know what the Borel sigma algebra of Rn is. Therefore you really should keep in mind that by definition of the Borel sigma algebra, it includes the topological structure, so what open means, into a sigma algebra. And in the case of Rn, this is indeed a really big sigma algebra, but it's not a power set. So it's not the biggest possible sigma algebra, but it's the most suitable sigma algebra in our context, because it contains all the sets we want to measure. And this is what we will do in the next video, where I want to define what a measure is. And there you will see that in the case of Rn, we need this Borel sigma algebra and can't choose the power set because our measure should fulfill some meaningful rules. And these rules can't be fulfilled on the whole power set, but on the Borel-Sigma algebra. And the Borel-Sigma algebra is big enough, there are a lot of sets inside, and indeed all the sets are inside we want to measure in the end. Then thank you very much and see you next time.
Guess which student has a better chance of getting into an Ivy League school? First, take a look at Zach. He's valedictorian.
Hello and welcome back to Hilbert Spaces, the video series where we talk a lot about the geometry such an inner product space gives us. And indeed, in today's part 8, we will continue with the important approximation formula which holds in Hilbert spaces. We will show the whole proof, and then you will also see why we need the assumptions we have stated. However, before we start with this technical explanation, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget, there are a lot of rewards for supporters, like early access to the videos or PDF versions for all the videos. Just click the link in the description to see what you can find. With that,
we often want our computers to be able to generate numbers that appear to be random. But what does it mean for a sequence to truly be random? If we take a look at some sample sequences of zeros and ones, we might ask, how random are they? Now, if we were to choose a sequence of zeros and ones of this length randomly, all of these sequences would have the same probability of being chosen, since all sequences of the same length are equally probable. But the fact that they're equally probable doesn't quite capture our intuitions about randomness. This sequence, for example, doesn't feel very random at all. It's just ones. This sequence also doesn't feel very random. There are zeros and ones, but they just alternate. Intuitively, this sequence feels pretty random. And what about this fourth sequence? Maybe it looks pretty random at first, but upon closer inspection, you might notice a pattern. A 1 followed by a 0, followed by 2 1s and 2 zeros, followed by 3 1s and 3 zeros, and so forth. And once you notice that pattern, this last sequence doesn't seem so random anymore. That intuition actually gives us a way to approximate what it means to be random. A random sequence in principle should be patternless. We shouldn't be able to identify regularities, like all ones, or consistent alternation, or growing runs of consecutive zeros and ones, or even less obvious patterns that might be harder to find. But what counts as a pattern? Well, in its simplest form, a pattern can be described. This sequence we could describe in English as 12 ones. This sequence we could describe as 6 ones and 6 zeros, but for something that feels more random, it's harder to describe. With this sequence, for example, it's hard to think of any simpler description than just writing out what all of the bits are. This then brings us to the concept of Kolmogorov complexity, a way to describe how much information it takes to represent some piece of data. Kolmogorov complexity is defined as the length of the shortest possible description of some piece of data. Of course, the length of the shortest possible description depends a lot on what language we're using to do the describing. So far, we've been using English to do the describing, but we could be a little more precise by using some programming language instead of a natural language. We'll use Python here, for example, but you could use any programming language. The question of Kolmogorov complexity now becomes a question of what's the shortest way you could write a Python expression that evaluates to the sequence in question. With all ones, the description is pretty short. We can just multiply the string 1 by some number. Alternating zeros and ones isn't much harder. Even something more complex, like our sequences of consecutive zeros and ones that grow in length after each iteration, can be described pretty succinctly in Python. But a sequence that appears more random? Again, it's hard to come up with a shorter description other than just writing down the sequence itself. There are a few details we'll gloss over here that often will use a binary description language to describe sequences of binary numbers, or that will often use some Turing machine for our description language to avoid unimportant differences between programming languages, for instance. But the key idea here is that we now have some metric, the Kolmogorov complexity, that quantifies how much pattern we can find in some sequence. And using this idea, we can come up with our own definition for what it means for a sequence to be random. A sequence is considered to be random, or more precisely, considered to be Kolmogorov random, if its Kolmogorov complexity is at least as long as the sequence itself. In other words, if we can't come up with a shorter description of the sequence than the sequence itself, then we can call that sequence Kolmogorov random. Kolmogorov complexity turns out to be a useful metric in a number of contexts. It's very related to the notion of the compression of data, for example, converting some longer representation of data into a shorter representation. But it also has its challenges. In particular, Kolmogorov complexity is uncomputable, which means not only is there no existing function that can take any sequence and determine its Kolmogorov complexity, it's been proven to be impossible for such a function to exist at all. The idea that not all functions can be computed is a fascinating one, and a topic worth exploring too, but for now, it means that it's impossible in general to calculate what the Kolmogorov complexity is for any given input. But Kolmogorov randomness isn't the only way to define what it means for a sequence to be random. How would you define randomness? What does it mean for some sequence to be patternless or unpredictable?